The question is, what are different ways to uniquely represent a two-dimensional force vector? Firstly, even though it's implied in the question, let us remind ourselves that force is a vector, just as velocity, acceleration, and displacement are vectors. You might recall from your physics that mass is a scalar, right? But force is a vector. So a vector has a magnitude and direction. Just for comparison, let's remind ourselves that a scalar such as a mass, density, cross-sectional area, length, volume, etc. only has a magnitude, no direction. A vector is a mathematical idea. It can be used to represent a force, a velocity, acceleration, or a displacement, right? A force, however, is a real quantity that we encounter in mechanics. A vector doesn't have a starting point. It only has a magnitude and direction. Whereas a force has both the magnitude and direction, but is also applied at a specific point. So if you're looking for one difference between the mathematical idea of a vector and a force, this is it. The force has a starting point. Let's consider what is called a two-dimensional Cartesian coordinate system. So what is a Cartesian coordinate system? Well, a rectangular coordinate system. A 2D system consists of two axes, two coordinate axes, x and y, and these two axes are perpendicular to each other. Since a vector has a direction, we need a coordinate system to represent its direction, right? So here we're going to use this 2D Cartesian coordinate system. Let's say there are three vectors, vector A, vector B, and vector C, like shown in this picture, and they are all parallel to each other and have the same length. Then the three vectors are equal to each other, even though the starting point of each of these vectors is different. On this picture here, I have a cantilever beam subjected to a force at a certain point A. So you can see we're starting to talk about a point where the force is acting, right? So we'll address the question of how to add two force vectors in a different video, but for now, it's sufficient to know that force is a vector and it can be represented as such. So let's talk about different ways to represent a force vector to answer the question. But we know force is a vector, right? And two-dimensional space, it has an x component and a y component, right? So these different methods we're going to talk about here are primarily for the purpose of communication. We'll talk about two different methods. This is the first method. And this method, we represent a force vector by its magnitude and an angle theta. Since force is a vector, I have a little underbar on the left side of this equation, right? This F that I have on the right side does not have an underbar, so we are using that to represent the magnitude. One of the common ways to represent the angle theta is shown in this picture. Theta is the angle that the vector F makes with respect to the positive x-axis in the counterclockwise direction. So in this first picture here, we have a force vector that has a magnitude of 15 Newton. You might recall that Newton is a unit of force in the SI unit system. The arrow here represents the direction of this force. Just to keep this general, I'm placing this force at this point, not at the origin. So how do we define this angle theta? Well, we superimpose the x and y axes at the starting point of the force vector. This is the positive direction of the x-axis, right? It goes from left to right, right? So you want to measure this angle from this x-axis in the counterclockwise direction, like shown by the arrow in this picture. So if you measured it from the negative axis, it would have been like that, right? That's not what you do. You measure it from the positive axis like this. So this force vector can be uniquely represented like this. The magnitude is 50 Newton and the angle is 50 degrees. So as long as you measure this in this standard way, you don't have to say how you measured this angle, because it's implied that you have measured it from the positive axis in the positive x-axis in the counterclockwise direction. So now you can see if I have a force like this, the magnitude is 50 Newton. The angle would be 120 degrees. Again, this 120 is measured in the standard way from the positive x-axis in the counterclockwise direction. For this force, the angle would be 300 degrees. For the same problem, if you decide to measure the angle in the clockwise direction, then you want to put a negative sign in front of that. Alright, so it will be minus 60 degrees. This is acceptable as well. The second way to represent a vector is to use its components. Say we have a vector f like shown in this first picture. We take this vector and resolve this in two perpendicular directions, one along the x-axis, the other along the y-axis. So to avoid confusion, you want to do a little construction like I have done here. First, superimpose the x and y axes at the starting point of the vector. Then find the projection of the force vector along the x-axis and along the y-axis. You also want to mark these arrows in these components because the signs are important, right? So if the arrow on the vector f is like this, the x component is going to have an arrow like that, and the y component is going to have an arrow like shown in this picture. On the other hand, if the vector f is like shown in the second picture right here, your x component is going to go in the negative x direction, whereas the y component is going in the positive y direction. Now you can follow these two pictures easily. Once you have done that, you represent the vector f in terms of its components like it's done here. You want to pay attention to both the magnitudes of the components and the directions. The magnitudes are the lengths of the sides of this little triangle. In this first example, this length is 12 pounds and this length is 10 pounds, and therefore vector f is 12, 10, and you put the units outside as well, pounds. The x component is positive because this arrow coincides with the positive direction of the x-axis, and the y component is also positive because this arrow right here coincides with the positive direction of the y-axis. Now let's look at the second picture here. This length is 6 pounds, this length is 8 pounds. So those are the magnitudes that go in this expression here. In terms of directions, you can see this arrow, the arrow for the x component is in the negative x direction, right? And therefore, you put a negative sign in front of that. But the y component, the arrow on the y component, is still in the positive y-axis. So there's a positive sign in front of that. Now you can easily follow these cases. And here we have a negative x and a negative y, because you can see this arrow goes in the negative x direction, right to left, and this arrow goes in the negative y direction, top to bottom, right? And in this fourth case, we have a positive x but negative y. So this serves to communicate in a unique manner. For example, if you tell me I have a vector f which has components 20 and minus 20 pounds, I will know exactly what you're talking about. There is another way to represent a vector in component form. This method utilizes what is called the unit vector. So let's go ahead and define what a unit vector is. Let's say with respect to a 2D Cartesian xy coordinate system, we have a vector A like shown in this picture. The unit vector along A is defined like this. Unit vector, usually we use the notation little u, equals vector A divided by the magnitude of A. When you divide or multiply a vector by a scalar, its direction doesn't change. So the direction of A and direction of u are the same. But what about the magnitude of the unit vector u? Magnitude of u will be 1 over A times the magnitude of the vector A, right? Which we know is also A. So A over A equals 1. Therefore, a unit vector has a magnitude of 1 or unity, and that's why we call it a unit vector. So any arbitrary vector can be represented in terms of its magnitude and a unit vector along it, just as A can be represented as this, right? By this method, vector A will be equal to its magnitude, which is A little a, without the underbar, right, multiplied by the unit vector along that vector, which is little u here, right? So here's a proof that it works. Little u is vector A divided by A, and you can cancel the magnitudes, little a, and then you end up with vector A, right? So we end up with vector A. We started with vector A and ended up with vector A. So the purpose of a unit vector is to represent the direction of a vector. So there's a unit vector in any direction, right? So let's call the unit vector in the direction of the x-axis as little I, and the unit vector along the y-axis as little j. Supposing, say, I have a vector that is in the direction of the x-axis like shown over here. This vector has a magnitude of little a, right? So if I want to represent this as a vector, then following this method of the unit vector, this little a, vector little a, will be equal to magnitude of that, which is little a, multiplied by the unit vector in that direction, right, which is little I. And similarly, if I have a vector which is in the direction of y and has a magnitude of little b, then that vector can be represented like this. Vector b equals b times little j. Now let's consider a general vector A, which has a component ax in the x direction and ay in the y direction. We have a little triangle here, right? So let's take the horizontal side of that triangle and define a vector in that direction. So by this method that we just talked about, right, that will be magnitude of that vector, which is ax, multiplied by the unit vector in that direction. And this line happens to be parallel to the x-axis, and therefore the unit vector along that axis, along that side of the triangle, is little I. And therefore that vector will be ax times I, right? Similarly, the vertical side can be represented by this vector ay times j. The vector A can be then represented by the sum of these two vectors. So vector A equals ax times I plus ay times j. So this is another way to write down a vector in its component form. Using the idea of this unit vector, we can take the four cases we considered in the earlier slide and represent the vector f, force vector f, like these. For example, in the first case, the components are 12 pounds and 10 pounds in the x and y directions respectively, right? And therefore the vector f will be equal to 12i plus 10j pounds, right? And in the second case, the components are minus 6 and 8 pounds, and therefore vector f will be equal to minus 6 times I plus 8j pounds, and so on. We will learn in one of the future videos that this method of representing a force vector gives us the most simple and efficient way to add multiple forces, something we have to do in solving static problems.